Okay, so I want to start now with an important construction of topological spaces, which uses this quotient space, which uses quotient spaces. So this is what are called cell complexes. So the basic idea is to build topological spaces from simple pieces. And these pieces are what we'll call cells. So a cell is, well, another name for the closed n-dimensional disk. So this is points in Rn of norm at most 1. And inside of here we have the points of norm equal to 1, which is the sphere of dimension 1 less. And so so then here's a general construction that one can do. So suppose you're given the setup, you're given a space X and a map from F to, from the n-1 sphere into X. And you consider the a partition on X disjoint union the n-dimensional disk, where so the subsets of this partition, so P, so there are subsets of the form X, f of X for X in the sphere, and then every other point is a singleton. So else, so this is either A is in X, but not in the image of F, or A is in the disk, but not in the boundary sphere. So we write well, let me write it this way. So X union over F dn for the quotient space P with the quotient topology. Okay, so we'll give it this special notation. Right, so some terminology. So here F is called an attaching map. And the procedure from going to X to this quotient space, this is called a cell attachment. So quotient or cell complexes are spaces that you can obtain from iteratively doing cell attachments. So let's start with some examples. So first, let's take X to be the circle, and let's fix some M integer at least 1 and consider the map F sub M from, well, let me suppress the M. So it's a map from the circle to itself, which sends, so F of E to the I theta is E to the I M theta. which is the same as e to the I theta to the m. So this is the mth power map. So for example, when m is equal to 1, f is just the identity map. When m is equal to 2, f is 2 to 1. So let me draw a picture in this case. So we have the circle mapping to itself via f. And well, each point has two preimages. So the point 1 has preimages 1 and minus 1, both 1 and minus 1 squared to 1, working in the complex numbers. And well, yeah, so every point has two preimages, which are antipodal. This is, yeah, basically because every complex number has two square roots. So e to the I theta is equal to, e to the I theta over 2 squared. And it's also equal to e to the I theta over 2 plus pi squared. So when you square, you get this 2 pi, and e to the 2 pi is 1. Okay. So then let's take z. Yeah, so let me erase this. So let's set z equal to be x, this quotient space. So we use this map f to attach a disk to the circle. So for example, in the case m is equal to 1, what we get, well, so we're not doing something so interesting. We're taking a circle and then we're attaching a disk to the boundary by the identity map. And so in this case, we get z is just the disk. In the case m is equal to 2, we get something slightly more interesting. So here we're attaching a disk to the circle by a 2 to 1 map. And well, so the picture to draw, one way to draw what this is in the following way. So we have a disk, and the boundary, well, points on the boundary are identified in antipodal pairs. And we've seen this space before. So this is the projective plane, RP2. Okay. And you could consider higher M to get some new spaces, which we haven't discussed. Okay, let's do a different example. So now let's take X to be a wedge of two circles, which is the space you get by taking two circles and joining them at a single point, like this. And for the attaching, we're going to attach a two-dimensional disk again. So we need to define an attaching map from the circle to X. And well, let me say informally how this, there's lots of choices. You can imagine, well, okay, so let me give these two circles names, A and B, and I'm going to orient them in this way. And so, well, we're mapping a circle into here. So you can imagine, some different maps. Like, for example, if you attach a disk along this circle, then the resulting space is going to look like a disk together with a circle like this. But you can choose more interesting maps. And well, okay, so the map, so let's attach along what I'm going to call A, B, A inverse, B inverse, which is to say that we first go along A, and then we go along B, and then we go along A in the backwards direction, and we go along B in the backwards direction. Okay, so it's maybe a little hard to tell what we're going to get, but let's draw the picture like this. So here's the disk that we're attaching. And if we just look along the boundary, so we go along A and then B, and then we go along A backwards and we go along B backwards. And this is a familiar space. So this is, as we've seen, the torus. And okay, so this shows that, well, okay, so here we see that the torus is obtained as a wedge of two circles from the wedge of two circles by attaching a two-dimensional disk. And right, so we could have picked really sort of any word here in A and B and their inverses and gotten a different space. So if instead we chose A, B inverse, then again, we get something that should look familiar. So now we have A, B, and then we go forward along A and backwards along B inverse, backwards along B. And so this gives the Klein bottle. Okay, so I hope at least the idea is clear for how this works. You start with a space and a map like this, and then you can attach disk along that map. And you topologize it as a quotient space. So the general definition is, so a space, well, let me say, a cell complex is a space obtained from a discrete set by attaching cells. Okay, so you start with some finite set of points with the discrete topology, and then you attach some cells, maybe, well, yeah, in some sort of way. So here, these examples here that I showed you are illustrating that you can obtain many of the surfaces that we've looked at already as cell complexes. And in fact, a theorem, which we should be able to prove later, says that in fact every surface is a cell complex. So it can be described in this way as building up from cells. So I want to mention another class of examples of cell complexes. So these are projective spaces. So last time we discussed the projective plane, And there's a higher dimensional analog of this, which is defined similarly. So RPN is, by definition, the set of lines through the origin in our Euclidean space of dimension n plus 1. Okay, so the thing I would like to explain, so as before, you view this as a quotient space of Rn plus 1 minus the origin, where you get a partition just in terms of lines through the origin with the quotient topology. So the thing I would like to explain now is, excuse me, is a theorem. I'm sorry. That RPN is a cell complex. Yeah, so I'd like to explain this, well, this concretely in the case n is equal to 3. So we already know this in the case n is equal to 2, because here's RP2. So let me show you how it works for n equals 3, and then you'll see the idea. So the way this is going to work is let's write, so we write points of RP3 as in this following notation, which I introduced last time. So this denotes the line through the point xy with coordinates xy, zw, and xy, zw is some non-zero vector, so not all of these are 0. And we understand that, well, if I multiply all the coordinates by some constant, then this gives the same line. Okay, so this is how we think of points in this projective space. And okay, so let me get a little more room here. So the starting observation for this cell structure is, well, we want to decompose RP3 into 2 pieces. And one way we can do that is, well, okay, so observe that we can write RP3 as a union of A and B. As a set, it's a disjoint union, where A is all of those points where W is equal to 0, and B is those points where W is not 0. Okay, so let's see what we can say about these individual pieces, and then we'll think about how they fit together. And from this, we'll see a cell structure. So first of all, A, well, what is A? So we're looking at lines in R4, and if the last coordinate is 0, that means this line is actually contained in R3. And so then we're just talking about the set of lines in R3, which is exactly the projective plane, which we've already looked at. Okay, so now we need to understand B. So claim is that B is topologically equivalent to three-dimensional space, which of course is which is equivalent to a ball, or the interior of the closed disk. Maybe I'll write it that way: the interior of the three-dimensional disk. Okay, so to see this, let's consider the following map. Which sends x, y, z, w to, so we want to point in R3. And the thing we know is that this w coordinate is non-zero. So we can get a vector, well, let's consider the following vector, whose coordinates are these quotients. And note that this is well defined. So if I had put A everywhere, then I would see A here and in the numerator and the denominator. And so it would define the same point. Okay, so this map is well defined. It doesn't depend on the particular point on the line that we choose to represent. So we have this map, and it has an inverse. Which sends x, y, and z to the tuple, so x, y, z, 1. And it's not so hard to see that these two maps are inverses of each other. And, well, also these maps are continuous. I'll leave that to you to check. Okay, so now we've decomposed the three-dimensional projective space into this space RP2, which we already know is a cell structure, together with some ball. And we'd like to say that the way these fit together topologically is like a cell attachment. And we'd like to figure out what that cell, how that cell attaches, what the attaching map is. So the claim is that RP3 is topologically equivalent to RP2 with a cell attachment, three-dimensional cell attached, where, so the map F here, remember, is a map from the boundary of the disk to RP2. And the claim is that this map is the quotient map. Let me say just from last time. So last time I mentioned that there's a description, there's a description of the projective plane as a quotient of the two-sphere. And so the claim is that if we consider that quotient map, then this is exactly, and then we attach a cell along that map, then that gives us the three-dimensional projective space. So let me explain the idea of this. So to understand how A and B are attached to one another, one should start with points in B that approach the boundary, that go to the boundary of the three-dimensional disk here. And so let's fix a point X, Y, Z in R3. And we're going to look at, so let's look at well, Tx, Ty, and Tz. Or rather, the image of this in B as t goes to plus or minus infinity. Okay, so and what we'll see is this will converge to, well, okay, let's just do the computation and we'll see directly. So so Tx, Ty, Tz, according to the map, this maps to the point, well, Tx, Ty, Tz1 in B, which is equal to, let's rewrite this, x, y, z, 1 over t. And so this converges to, so this converges to x, y, z, 0 as t goes to either infinity or minus infinity. And so this is a point in A here, which is RP2. And so, well, we see what's happening is, well, okay, so I mean, this is giving us a description of RP3. So we have this three-dimensional ball. So this ball is filled in. So here's B. And we know that as we go towards the boundary of B, this point, well, these antipodal points on the boundary are identified. That's sort of what this statement is saying. As we go so this is like in the direction X, Y, Z in R3, and as we go, as we approach the boundary here, I'm not saying this the best way, but this point and its antipodal point are both glued to this point here in RP2. Okay, so I'm trying really just to convey the idea here. And so this is the idea. And so let me just point out that this description of the three-dimensional projective space as a quotient of a ball modulo antipodal points on the boundary is entirely analogous to what we saw for the projective plane last time. So remark, this is analogous, this description of RP3 as a quotient of D3 is analogous to the description of RP2 as a quotient of the two-dimensional disk. So here you think of, here the two-dimensional disk was appearing as for RP2, the two-dimensional disk was the upper hemisphere. Sorry, that's my cat. Lucky. And so in this analogy, you should think of the three-dimensional disk as the upper hemisphere in the three-dimensional sphere. So everything's one dimension up. And so here, points on the boundary of this disk are identified in antipodal points, since sort of lines through the origin that are in this plane pass through 2 points here. And okay, so this is the same thing that happens one dimension up. Okay, so I think that's all I want to say about that, at least for now. Yeah, so let's, in the remaining time, talk about something a little different. So orbit spaces. So in the last lecture, I think I promised to bring this discussion of topological groups and group actions back, or connected to quotient spaces, and so we're going to do that now. So recall from last time that a group action is a function of the following form. So G is a group and X is a space. We have some function like this, which we write as G dot X. And it has the a few properties. So first of all, for each G and G, the function X goes to GX is a topological equivalence. Sorry, my pen is being slow. A topological equivalence. And well, if I take a product of two elements in G and act on X, then this is the same as acting first by H and then acting on that by G. Okay, so some examples that I want to look at now. So some examples to keep in mind. Let's take G to be Z squared. Acting on X is R squared by translations. So NM integers acts on a point XY by translating like this. Yeah, so let me just give you a couple of actions. G is Z mod 2Z, cyclic group of order 2, acts on the two-sphere by the antipodal map, well, the non-trivial element acts as the antipodal map, so x goes to minus x. And then, well, yeah, so one remark is that a given group can act on a given space in many different ways. That's already true for both of these examples. But here's, let's take G, again, Z mod 2Z, and X to be the torus. And let's consider a few different actions. So here's, I'll draw them as pictures. Well, okay, let me draw three tori here. So I want actions by a group of order 2. So basically the two things we can do are we can rotate and we can pick a certain axis of rotation, or we can reflect. Let's reflect something like this. So here we rotate by pi in both of these pictures. So for example, in this picture, like this green curve gets sent to this green curve under the map. In this picture, like this curve gets sent to this curve, and this curve here is fixed. It's preserved when this is like you take a skewer and you just rotate it along this skewer. And then in this case, we have these two are fixed pointwise, and we're doing a reflection here. So this defines a Z mod 2 group action, because if we do this transformation twice, we get to the identity. Okay, so we'll revisit these examples in a second. I want to first give you a definition. So let's say G acts on X. So for a point X, little x and X, the orbit of X is the set, so it's denoted O sub X, and it's all of the points that you can get by applying a group element to X. So it's Gx, where G ranges over points in G. And a basic observation is that orbits are either disjoint or equal. So that is to say, if the intersection of two orbits is non-empty, then in fact these orbits are the same. So I'm going to let you think about this as an exercise. It's a good exercise. It's not so bad. But what this means is that we can form a partition from these orbits. So P, consisting of the subsets, which are the orbits ranging over points in X, this is a partition of X. So we'll write x mod g for this partition with the quotient topology. Okay, so in this way, given a group action, the orbit, so this is called the orbit space. Given a group action on a space X, we can consider the orbit space. This is the set of orbits, which we can topologize as a quotient. So this is a useful construction. Let me give you some examples to get a feel for how this looks. And I'm going to do this a little bit informally. So let's return to these examples that we had before. Maybe I can just take this page, copy it. Okay. All right. Right. So this first example, let's take this action on the plane by translations. I'm sorry if you hear a lot of running. My cat is going absolutely crazy. Oh, you know what? I didn't write this example in my notes. But I do want to say something about it. So here it's useful to observe that, well, every orbit is of the form O sub xy, where xy lies in the square 0, 1 squared. So the reasoning here is that, well, so if we're in the plane, so we have the plane and the action of z squared preserves this integer lattice. And well, if you have any point in the plane, then, you know, by a sequence of, well, yeah, by some translations, horizontal and vertical, you can move it to, I mean, I guess, sorry, this is inefficient. So whatever this point is, you can, you know, translate it by some amount, and then horizontally, and then some amount vertically to get it into this region here, which is this set 0, 1 squared. And right, and then the next thing to observe is that, well, under translations, this edge is identified with this edge, and this edge is identified with this edge. So what you conclude from all of this is that the quotient space x mod g is actually topologically equivalent to the torus, which we've seen now in several guises. Okay. Let me also treat the other examples that I had before. So the next one was G is Z mod 2Z acting on x is S2, which is antipodal by the antipodal map. So here are the orbits. So the orbit of x, well, the action is antipodal. It's exactly x and minus x. So the partition we get is a familiar partition. This is the partition that we saw last time, which gives the quotient of S2, the corresponding quotient space is the projective plane. So here we see that, I mean, this is exactly what we saw last time, that if you take S2 and you identify antipodal points, this is the space of lines through the origin. Every line meets in exactly 2 points. So if you identify those 2 points, you get exactly RP2. Okay, and then let's just see pictorially what quotient spaces we get for these, for the last example. Since I already drew them, maybe I can just pull them up and not redraw them. No. Okay. Oops. Okay. Oh yeah, I guess I want to erase that anyway. Okay. Nope. Okay. Okay, so we have these 3 different actions. Let's think about what the quotient space that we get is. And I'm just going to draw some pictures, which, well, let's see if I can convince you. So we're going to do similar to how we did with this action. If you want to identify the orbit space, it's a good idea to try to find some subset which contains exactly 1 point in each orbit, maybe with the exception of points on the boundary, and that will give you some gluing instructions. Okay, so we'll do that here. So here we have this Z-mod 2 rotation by pi about this axis, which we said sends this green curve here to this green curve. And it sends every point on this side to a point on the other side. So in fact, this region in the front here has the property that I was saying. It contains 1 point in each orbit except for on the boundary. So this green curve on the boundary is identified with this other one over here. So this, I guess now I'm drawing it in yellow. These 2 curves are identified. That's really hard to see. But what we get from that is the torus. So here, x mod g is the torus. So we take those 2 green curves and then we join them back together and we have something like a smaller torus. Okay, so that's what happens in this case. So in this case, okay, so we said that this, so in this picture, these 2 green curves get mapped to each other. We're trying to find 1 point in each orbit. So let me, excuse me, let me do it a little differently. We said the red curve is mapped to itself. And similarly, this green curve here is mapped to itself. And yeah, all of these points in the front are sent to points on the other side, back here in this region. And so what we see is that the quotient is Well, the other thing to observe is that this little arc on top, when you do this flipping motion, it gets identified with this edge down here. And similarly, this gets identified with this edge down below on the back side from this perspective. And okay, so with a little bit of thought, what you find is that this quotient is the two-dimensional sphere. And in the sphere, you see sort of the image of these 4 points. So you have somewhere here 4 points like this, and the image of the red circle is an arc like this. Sort of gets folded in two, and similarly for the green circle. Okay, let's do this last example. So here, the red and these two red curves are fixed pointwise by this reflection. We're doing a reflection across this plane that I'm drawn here. Yeah, so a fundamental, well, okay, yeah. So this region on the right contains 1 point in each orbit. This green part gets sent over to the other side. And in fact, yeah, I mean, each of the points on these red circles is their own orbit. So because these points are fixed by the group action. So here, x mod g is, so it's an annulus. It looks like this. So that's like, so okay, so this is S2 and this is S1 times an interval. Okay, so okay, so we'll stop there, and next week we'll continue with a little bit more of quotient spaces, and then move on to the next part of the course.